Well, hey, thank you. I'm excited to be here today and talk about what we've done with Kubernetes. I hope that everybody can get some value out of it as well, and that's why I want you to know that feel free to ask questions anytime. I'll stop if there's too many questions so that we don't run out of time and you can actually eat at some point. So we're going to talk about why we picked Kubernetes. We're going to talk about why we picked CoreOS, and then talk about our multi-cluster architecture and some of the things we learned in going through this process. So thank you, Redbeard, for the great introduction on Concur. Just a little bit more data around our company here. What's really important to us, though, more than anything else, is our end users, and that they have a good experience using our products. And our adoption has been tremendous, and it's actually accelerated with the acquisition of our company by SAP. So we have a lot of end users, thankfully, and we want to make sure that whatever tools or technologies that we use, we don't impact those end users, that they can still get reimbursed quickly when they're still on the road, that they have a good travel experience when they're using products like TripIt, for example. So quickly, a little bit about me. I've been focused on Kubernetes for the last year and a half, and in various roles at Concur. I've been there a long time. Some people ask, why are you still there? You've been there for 17 years. But the answer to that's simple. I've been in a lot of different roles over the years, and it's been challenging and fun. So why go anywhere else? So moving on. Why did we pick Kubernetes? I don't need to drain all these points. I think you've heard it over and over again from the various other presenters. But there's a few things here that I want to specifically call out that are really important to us. One is that with the container systems that are available today, we needed some level of protection from potential changes to the ecosystem. And if you're using a platform that's 100% open source, you have that protection. You can already see that you could use Kubernetes with multiple container runtimes. And that was extremely important to us because if we're going to go through the process of retooling for containers, we don't want to have to go through that process over and over again as technology changes. There is some overhead to dev teams when they go through this process, right? I absolutely want to get the same value out of this platform that we're seeing from Ticketmaster mentioned, where dev teams don't have to continuously rewrite imperative script in order to deploy their services onto VMs. But there is some overhead in rewriting and Dockerizing as well. So if they're going to go through that process, let's make sure they don't have to do it again. And then the other thing that I think is really important with this platform is the pluggable API. And I'll talk a little bit more about that later on. So then, why did we pick CoreOS? Well, there's a few points here, but you can read, obviously. But the most important one for us, we were on a Linux version that just barely didn't make it to Docker support due to the kernel version. And we were going to have to do a bunch of work to move to a newer version of systemd in order to support Linux containers in order to run Docker. So if we're going to go through that process anyways, then why should we continue to use the same operating system that was always going to be behind by significant numbers of kernel versions and not be able to continue to adopt the latest Docker features into the platform? And then on top of that, the ecosystem around Docker containers is really complicated. There's a lot of different pieces that need to fit together and be at the right version. So I think the best analogy I could come up with for this is a hypercar. So in a hypercar, you've got an engine, you've got motors, a bunch of sensors, all kinds of electronics. They all have to work together and be tuned extremely well in order to run at optimal performance. And the Docker ecosystem's the same way. You've got Flannel and etcd and systemd and the kernel, and they all have different versions. They're all getting developed by the community at different paces. And how do you know which versions work with each other? Well, you want to make sure that when you put this whole platform together, that you're driving a container environment that's a little bit more like the way Jeremy Clarkson drives than the way James May drives. If you don't understand the reference, it's a Top Gear reference. You should definitely check out the show or their new Grand Tour show on Amazon. Sorry for the plug. I'm from Seattle. Got to plug Amazon. So CoreOS makes this really easy. And what we found is that looking at the CoreOS process for the way that they do these releases, they've already tested the specific versions of each of these pieces with their version of the operating system. And they're very up to date. I mean, look at the kernel version that's there. And you've heard about this process from the CoreOS team as well, and I'm sure they can speak to it a lot better than I can. But for us, as we were figuring out how this would work in our environment, it made it really easy for us to know that we were going to pick pieces that had already been tested and would work together. So it really lowers that bar for you when you're starting on this journey. You don't have to go piece together the supercar on your own. So with that, I'll start talking about high availability a little bit. And the Kubernetes community has put together this great guide on how to make clusters highly available. It talks about having multiple nodes of etcd and the API servers and whatever else. It's a good guide. It's very useful. But the thing is, every clustered technology, in particular new technologies that haven't been well run or run in a lot of places for a long period of time yet, have the potential for failure. And because of that, we needed to protect from possible failures, and we needed to consider this as a part of our architecture. How are we going to do this? So just speaking a little bit more about the failures, it's a great, I'm not going to say, oh, absolutely, it's going to fail. It's a great system, right? You heard about etcd and the way it was put together, and the way that you can have the multiple API servers. So it is a good system, but with any system, there's unknowns. And that's what we wanted to protect ourselves against here. For example, there's different classes of problems, right? There's known issues with things that you can monitor for, like how much CPU or I/O the system is consuming. You know, if you hit a certain point, you're going to have performance issues. That's a very well-known issue. Well, there's also known unknowns. Things like, I know that MySQL is going to have a lock contention issue at some point on this table if I keep throwing workload at it. I don't know exactly when it's going to happen, but I know it could happen because I've seen the experience from other people hitting this issue in the marketplace. So I can monitor for it, and if I start to see indications that it could be happening, then I can architect around it, move workload off the table, optimize my queries, whatever it is. That's a known unknown. Well, with new technology, there's always unknowns like that you don't know about yet. You don't know what to look for or how it could possibly fail because not enough people have run into that problem. So what we did is we went with a multi-cluster architecture where we had multiple Kubernetes clusters in every location in order to protect against this potential for failure. This is an example of our CI pipeline that we use for new microservices in our environment. Not everybody uses this exact pipeline. And I'll talk through some of the tools. I'm sure some of you are like, what's that penguin up there? We'll talk about that later. We use Yeoman to scaffold. So new teams, as they're getting started, can pick their programming language, whether it's Golang or Java or .NET or whatever else. And we have templates for each of those programming languages. When they use Yeoman, which is, like I said, just a scaffolding tool, it builds out that project and pushes it to GitHub, our internal GitHub enterprise. Well, with that scaffolding, it includes all of the information to pass on to the CI system about how to deploy and build the Docker container and push it out to our Artifactory repo, which is where we store the Docker images. That's where you see staging at the top. That's Artifactory. Well, then it also promotes an Artifactory from the CI system and then makes a call out to the penguin there, which is Skipper. And we'll talk about what Skipper does a little bit later, but eventually ends up in Kubernetes. So this, once again, is an example of what the architecture looks like in our data centers. This isn't an exact replica of what it is, but for each location, we have different zones and a Kubernetes cluster for each zone. Well, let's zoom in a little bit here. So how did these get wired together? What I show here is 2 clusters instead of 3, again, for simplicity. But what we had to do is a couple of things. We had to take any of the monitoring tools for Kubernetes and pull them outside. So Prometheus and Elk, we run externally. And then we had to tie in the worker nodes to load balancers so that requests for services could make it to the different Kubernetes clusters. And we still had to build each cluster so that it was highly available. So we still have multiple etcd nodes and multiple API servers to keep the system up and running as much as possible and learn about how to prevent the unknowns, the unknown unknowns, so that eventually we can move to a single cluster architecture in our data centers. But how does that work? How do you connect Kubernetes up to a load balancer inside your data center? That's not easy, right? So this is what we did. We built our own plugin. And this is a simple Golang binary that runs in the Kubernetes cluster. Each of the clusters has its own copy of this. And it watches the Kubernetes API. Each one of the resources in Kubernetes has a watch endpoint. And when you hit that endpoint, it creates a long-lived HTTP connection and pushes any updates to that resource to you. So within the Golang binary, it watches for changes to services, changes to nodes, and then if it sees a change to a service that is of type load balancer, it calls our own internal API for load balancing and creates the necessary VIPs and pools to route traffic to the containers on the cluster. Likewise, if a node is added or removed from the cluster, it makes the appropriate calls to all of the pools to add and remove that node so that the pools are updated and traffic can go to the new node or not go to the old node. So we also did a few unique things here, but the goal was to make it so deploying to Kubernetes in a cloud environment looked the same as deploying to Kubernetes inside our data center. All that teams have to do is have type equal load balancer for their service object, and the API knows to just plug it in the same way it works inside a cloud environment. But how does this help you guys? What we did is built a example project for this out on GitHub. It's publicly available. So you can see how to, with Golang, connect up to the Kubernetes API, get those events, and then run whatever business logic you need to run inside your data center. Maybe it's calling an API that just is a change API. Maybe it is something similar to what we've done with tying it into your own custom load balancing solution. But whatever it is, our goal here is to give back and help lower the bar so that other folks can do similar things to what we've done. By the way, I love writing Golang, and it's a lot of fun to put Golang in Docker containers and run it on Kubernetes. You can create really small containers from scratch. If anybody ever wants to geek out about that, let me know. I'd be happy to geek out. OK, so that takes care of load balancing. What about upgrades of Kubernetes? Well, we started our journey a long time ago on this, a long time ago in tech terms. And the operator wasn't even being talked about then. So, and even still, I don't think you can use the operator to actually upgrade all of the components of Kubernetes at this point. I think we'll get there. So how do we do this? What we decided to do is take the same approach that we use for any of our services that get deployed and blue-green the clusters. So when we're ready to go to the next version, we create a whole new set of Kubernetes clusters that's on the next version, and we deploy all of the services to all of the clusters then at that point. All of these, for example, in the US location, would be tied into the load balancing tier. So requests can hit everything. And then if we identify an issue, well, we just kill all the nodes on the new cluster. And if we're satisfied with the newer version that we deployed, well, we kill the old version. So we have a really good rollback strategy. But that's not easy either. How are you going to get all of your stuff on all of those clusters? What we found is that everybody had these kubectl scripts in their GitHub projects that would be picked up by the CI and run their JSON or YAML that they had come up with against the Kubernetes environment, which was cool, right? It's a really nice, slick way of getting things deployed in a continuous delivery fashion, but it has a lot of challenges. Everybody has to keep those things updated. We ended up with hundreds of different versions of these scripts in the environment, and everybody would ping me if something didn't work anymore. Hey, Dan, how come this SEA cluster is giving this error? Well, it's because that cluster doesn't exist anymore. Can you help me change the YAML so that I'm no longer deploying a pod or a replication controller, I'm deploying a deployment, right? So we didn't want to have to maintain all that stuff anymore, and also a few other issues there. So what we decided to do is write our own thin layer on top of Kubernetes that I call Skipper. And what this is a simple API layer that abstracts this from the CI system. So when it's ready to deploy a container to Kubernetes, it just does a curl. And it says, here's the container, here's how many copies I need of it, and which location it needs to be deployed to. Then the Skipper layer, what it does is it fills out the Kubernetes YAML on behalf of the request and figures out where it needs to get deployed to, makes all of the Kubernetes API calls to the Kubernetes clusters. Once again, Kubernetes got a great API. So then if we come out with test 14 D cluster or test 15A, B, and C, nothing needs to change in the CI system. It's still doing a deployment to test. And likewise, if the CI system wants to deploy the container to prod, it's just changing test to prod, just a different location, and nobody needs to know what all the actual clusters are in the environment. Well, this worked well, and everybody liked it, so we started adding more features to it. So we made it easy for ops to update the configuration that it uses to decide what clusters are available, so that when ops builds out a new Kubernetes cluster, they can just curl the skipper API and put it in there. Or if one is, they identify some issues with one, they can take it out, so no new deployments go there. And this is a cool feature that we added, which makes it so as a dev engineer or someone that's looking at the services running on Kubernetes, they can easily get that kubeconfig written to their local kubectl config, right? All they have to do is curl skipper. It's already got all the metadata about what clusters are available, and it spits out a bunch of bash commands that build out that configuration locally in a way that doesn't overwrite your file. So if the developer has their own Minikube environment or other clusters that they're maintaining themselves for testing, they still have those in the config. OK, so we added features, and Skipper started to get a little fat. It was supposed to be a thin layer. So what do we do about that? Well, we're starting now to take the features that we implemented in this internal API and push them upstream. So for example, one of the features I'm working on is making it so there are labels that you can deploy to with federation. So you get the same abstraction from your CI system. You can just deploy to test or deploy to prod with federation, and it only goes to a subset of the federated clusters instead of to all of them, like it does today. And this will be available in 1.6, assuming I can get my Golang code working right. And then some of the other features listed there we'll continue to push out to the community as well. I also put the docs for the API out on GitHub if anybody's interested in how the API works. I still like this layer of abstraction in our environment, and most likely it will stay unless we can get all of the compatibility that we need into federation. But one of the other things it gives us is, 10 years from now, should we move to some other orchestration technology that's like way cooler than what we have now, if we're already using an internal API, we could easily update it and have it deploy to that new technology that we can't even imagine how awesome it would be today. Maybe it's unikernels or something else. So here's a little look into one of the Kubernetes clusters in our environment and the number of updates that developers are making to services running on there. Each metric there is one deployment of one service. So as you can see, it's up and to the right here. So our adoption is pretty good. We don't have everything broken apart from our monolith yet, obviously. But as we do that, more and more things get pushed to Kubernetes. It's going to be a long road, though, to get there, as anybody who's done microservices knows. But I think what's important here is we're starting to see that value in the platform because the teams can iterate a lot faster using this full CI process end-to-end deploying to Kubernetes than they could with any other technology available today. So with that, definitely would like to open it up for questions. One thing I would say is you might look at this and say, wow, that's crazy. Why would you have so many Kubernetes clusters? And why wouldn't you just really, really make sure that it's highly available? And that's fine. This isn't an architecture for everybody. It's definitely not the perfect architecture either. We're still iterating on this. In fact, some of the things that I showed, we've already started to consider changing, like our integration to our internal load balancing tier. We're looking at ingress, which wasn't available when we started this. But like I said, we'll keep iterating and try to keep making it better. Anyone think of a question?
One question.
Just a second.
Where do you run your cluster, and what's your security model for it?
So we run our clusters inside our data centers primarily. We do have some clusters in cloud providers. Most of the ones in cloud providers are only for internal development and QA. The security model that we have is a RBAC model. So with Kubernetes, you can assign permissions via client certs or tokens to a specific namespace. So that's the model we went with, so that we can lock down each namespace separately. And in our environment, a namespace is a dev team or a GitHub org. Does that answer? OK. Any other questions? OK. Well, if there's no more, I'll leave time for someone else so that you can get to lunch earlier. So.
Thank you so much, Dan. That was
Thank
absolutely.
you.
Good job.